Hello, I'm Chen Yuzhu. This is my final project presentation for CS358 Parallel Computing. The topic is to create a maze and then solve it. So in this presentation, I will contain project motivation, system overview, how I generate a maze, and how I sped up the process. The result, which contains a demo video, and an explanation to Amdahl's law. So this project comes from one of my previous projects. It generates a maze and then solve it. It is actually a very interesting and classic problem. During running the program, I noticed that it took almost no time for the maze solver to solve the maze. But the maze generator took a very long time to generate the maze. Therefore, when I was first writing the code, I was thinking of improving the algorithm. However, I then realized that I was already using one of the most popular algorithms to generate a maze, so I have no clue what to do at that time. So in this program, it gives me a chance to speed up the generation process. Instead of improving the algorithm, I use parallel computing to speed it up. So this is what my maze look like in terminal. I use hexagonal design to make it look cooler and fancier. And you can see this. So this is already solved maze. So in the terminal, the walls are red, and the free cells, which are the non-wall cells, are white, and the path is green, and the starting point and ending point of the path is blue. It might not look it might look invisible in the terminal because it's very messy, but yeah, but that doesn't matter because we are focusing on the generating process. Because yeah, we can see in the terminal that it takes much more time to generate a maze than to solve it, no matter how big the maze is. So for the uppercase, it is generating a 100 by 100 maze. It takes 21 seconds to generate it, and it spends only less than 0.01 seconds to solve that. For the lower case, when we have 200 by 200 maze, it takes more than 5 minutes to generate it, but it still takes about 0.01 seconds to solve that. So we realize that the bottleneck is actually creating the maze instead of pathfinding. So I chose to parallelize the generating maze, as it takes a lot of time to run, and I also chose to leave the pathfinding section as it was because it is already very quick. Because we know that for parallel computing, if a sequential section is working fast enough, making it parallel will not essentially make it faster, but expose it to the risks like race condition. Okay, now let's take a look at the maze generation. So on the left, it is a block diagram, and on the right, it is the pseudocode of what I have in my program. So the first step is to create an R by C maze, and in which it contains all the cells are walls, and then we randomly pick one of the cell and set it as a non-wall cell. So this becomes the starting point of the whole maze. And then remember that I chose to have a very fancy hexagonal maze. So for each cell, it always have 6 adjacent neighbor cells. So we add these 6 adjacent neighbor cells to the frontier list, and we judge if the frontier list is empty or not. If it's empty, then we start the loop. We add all potential wall cells, which only have one free neighbor cell, into the candidate list. Then we randomly choose one candidate and mark that as free. Finally, we remove it from frontier and add its wall neighbors. And then we start a new iteration. So we iterate it again and again till the index exceeds the max step, and then we stop. To parallelize this section, we notice that only 2 steps can be parallelized. So one of them is when creating a maze full of walls, and another is when looking for potential wall cells. So for creating a maze full of walls, it is fully independent operations. Therefore, each cell can be initialized in parallel. And when checking frontier cells to find valid candidates, which is the part that takes a lot of time, so it will be very worthwhile to parallelize it. And luckily, it can be each frontier cells can be evaluated independently, so it is very suitable to parallelize. So this is a demo of the parallelized code. I set it a little bit. I set the maze a little bit larger so that we can have a clearer idea of how fast it speeds up. So now we're running in one core, using one core, and let's see how long it takes. Okay, it takes a long time. It takes almost half a minute. So let's see how long it takes for 2 cores. So now it's much faster. It takes around 16 seconds. And let's see for 4 cores. 11.7 seconds, even faster. And for 8 cores, 8.5 seconds, still increasing its speed. So for 16 cores it takes 7 seconds, and for 32 cores it takes 6 seconds. It's becoming closer. And okay, 64 cores it takes around 5 seconds. So we can see it is getting faster and faster, but the accelerating rate is decreasing. Okay, so after running the parallelized program to create a maze of different size, we can see it is much faster than how it was. So for the upper case, we are still running the 100 by 100 maze. And for the lower case, we're running 200 by 200 maze. It still takes some time to run for when we have more than 1 course, but it is already much faster and saves a lot of time. And we also notice that as core amount increase, its speeding up rate also decreases. So that is due to the existence of sequential section. So the speed up performance is limited. The fast time it takes would depend on the time sequential section takes. So let's say in the ideal case, we have infinite amount of cores. So in this case, we have it would take almost no time, like 0 second, to actually solve the parallel section. but for the sequential section, it is not sped up, so it will take the same time. So eventually, the speed up rate it will be limited. So this is the end of my presentation. Thank you.